Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X published on August 11th, 2025, about 4 days ago. The standout result is that a minimalist recipe, advantage normalization plus token-level loss aggregation, reliably unlocks learning and critic-free PPO and outperforms heavier setups like GRPO and DAPO. The paper is titled Part 1, Tricks or Traps, a deep dive into RL for LLM reasoning, and the implications for model training are quite significant. Beyond that, the study demystifies normalization, clipping, filtering, and loss aggregation through controlled ablations in a unified open-source framework across models, datasets, and math benchmarks. Building on that, tweets highlight a rigorous, unified review of reinforcement learning tricks for reasoning, praising empirical depth and spotlighting advantage normalization as the key insight. One post emphasizes light PPO beating heavier recipes. Engagement looks strong on the first tweet with about 600 likes. Alright, this figure sets the stage. On the left, a wheel of techniques shows the crowded option space, spanning normalization, clipping, loss aggregation, and data filtering, which explains why choices feel overwhelming. On the right, two training curves compare methods. The red light PPO line steadily rises and stays stable, while GRPO and DAPO wobble or collapse late. Building on our intro, the message is clear. Fewer, well-chosen tricks deliver higher accuracy and more reliable learning. Okay, focus on this bar chart that profiles dataset difficulty by how many correct answers appear within 8 rollouts. The top easy row skews heavily to 6 to 8 correct, meaning prompts are often solved repeatedly. The medium row shows a mixed spread, with many prompts yielding 0 to 3 correct and fewer high counts. The hard row concentrates on 0 to 3 correct, with only a modest slice reaching 4 or more. This distribution justifies the easy, medium, hard splits and foreshadows longer outputs on tougher sets. Next, these grids of accuracy curves compare normalization choices across models and datasets. The red group-level normalization lines climb smoothly and finish highest on both 4 billion and 8 billion base models for easy and hard sets. The blue batch-level normalization lines sometimes lag or dip, especially when batches are skewed. In the bottom grids with aligned models, both methods look similar, but group-level normalization still holds steady, avoiding collapses. The legend clarifies that gray traces show no normalization, which converges slower and less reliably. Now, this multi-panel figure probes the standard deviation term in normalization. First, look at the large left plot, where reward variability on easy data collapses quickly, while hard data stays high. Moving to the right panels, removing the standard deviation on easy data boosts accuracy and avoids late training crashes. Then, in the bottom row trained on hard data, curves with and without the standard deviation nearly overlap, indicating similar stability when rewards remain diverse. Next, this multi-panel figure compares two clip upper bounds, gray at 0.2 and purple at 0.28, across models and math benchmarks. Notice the top block with base models shows tiny or negative gains, which aligns with limited exploration capacity. Moving to the lower blocks with aligned models, the purple curves hold higher accuracy and resist late dips, especially on AIME and Minerva Math. The consistent separation suggests higher clipping slows entropy collapse and supports better solution path discovery. Moving to these panels, we compare token-level versus sequence-level loss aggregation. The upper block with base models shows blue token-level curves rising faster and finishing higher across most benchmarks, especially on harder data. Shifting to the lower block with aligned models, the gray sequence-level curves lead, with quicker convergence and better final accuracy. This contrast supports the guideline. Equalizing per-token gradients helps base models, while preserving whole response structure benefits aligned models. Alright, focus on this composite figure showing accuracy over training steps for two base models, 4 billion and 8 billion, across 6 math benchmarks and 2 difficulty tiers. The red light PPO curves climb steadily and then hold, while blue DAPO and cyan GRPO often peak early and collapse, especially on hard sets. Building on our earlier points, the gain is largest for small models lacking stable reasoning, and it persists on 8 billion with hard data where longer outputs appear. Building on that, 2 takeaways stand out. First, context matters, where group-level advantage normalization and carefully chosen clipping shape stability and exploration. Second, simplicity wins, since light PPO, combining normalization and token-level loss aggregation, consistently beat heavier baselines. Advantage normalization means centering rewards to stabilize gradients. Thanks for listening. I am Alex, signing off.